Welcome back, everyone. This is Dr. Gallenstein, and we are here again with lecture number 13. Okay, in lecture number 13, we're going to look at something called panel data. Okay, and this lecture is going to partly be a continuation of what we've been looking at. That is, tools for how to solve the omitted variable bias problem. But then, in another respect, this lecture is also going to broaden our understanding of data. So far in the class, we've worked only with what's called cross-sectional data, which I'll talk more about in a moment. Cross-sectional data is data that has a bunch of observations for different individuals, typically, at one moment in time. And what we're going to look at today is, what if we have data that also has a time dimension, a time dynamic? What if we have data that is multiple people, but across multiple time periods? So we want to introduce what that data would look like and what data like that allows us to do in order to solve that omitted variable bias problem. In fact, we will find that when we have that kind of data, there are certain things that we can control for that we weren't able to control for in the past, which helps move us closer to that to solving that omitted variable bias problem. Okay, so that's kind of the overview here. We're going to learn about panel data, and then we'll learn some tools that we can use when we have panel data to solve that omitted variable bias problem. Okay, so with that introduction, let's dive right in. All right, so introduction. Often when we seek to answer a research question, we are not only interested in differences between people or some other observational unit. We tend to work with people a lot in this class, and so I'll just refer to them as individuals, but it could be, differences between cities or villages or, some other unit of observation, some sort of observational unit. But I say, usually when we answer a research question, we're not only interested in differences between people, but we're also interested in differences across time. Sometimes we might want to know the impact of a program before and after it is implemented. We might want to know how education affects wages differently at different points in time. If we want to know how variables change over time, we need to incorporate more than just one time period of data. And so that's what we're going to do today. So let me define some things. Cross-sectional data, I mentioned it before. Cross-sectional data is a data set that contains information on multiple observational units, like I said, individuals, groups, cities, countries, villages, etc. It has information on multiple observational units, so on multiple people at a single point in time. So there's one unit of time, multiple units of observations, so multiple people. This has been exclusively the type of data that we've looked at so far in the course. We have looked exclusively at cross-sectional data. Many times we've looked at data sets of smallholder farmers in a village. The data set was collected at one period in time and measured and collected information on multiple different people. That's cross-sectional data. Now, there's another kind of data called time series data, which is not covered in this course. Time series data is a data set that contains information on a single observational unit, it could be a person or a country or a village, over many periods of time. So instead of doing multiple people at one period of time, time series data does one person at multiple periods of time. All right. And then lastly, and this will be the topic of today, there's something called panel data. Panel data is a data set that contains information for multiple observational units, so for multiple people, over multiple periods of time. So panel data is a series of cross-sectional data sets collected on the same people over multiple periods of time. So panel data kind of combines cross-sectional data and time series data. Panel data is a powerful tool, which we will see. But now to drive this point home, let me just try to make sure that it's clear what I'm talking about when I talk about these different kinds of data. Specifically, I want to talk about what does cross-sectional data look like and what does panel data look like. Okay, so we'll just use an example. So imagine we're studying the impact of education on individuals' wages. We could collect a cross-sectional data set in which we collect data on multiple people's wages at the same point of time. And that would look a little bit like this, where we have multiple people, so person 1, person 2, person 3, person 4, and then we have information on their wage and information on their education level. All of this was collected at one point in time. So there's no reason to have a variable that indicates the time because this was all collected at the same point of time. Okay, so this is cross-sectional data. This should look very familiar because we've used cross-sectional data throughout the course so far. But now, what if we collected data on the same people more than once? We could collect data on the same people twice, which would allow us to capture changes in these individuals' outcomes over time. We could see if wages are increasing or decreasing over time. See if the impact of education changes over time. See if increases in education would have an impact on wages, etc. So we call this panel data. Panel data is when we have more than 1 year of cross-sectional data for the same people. All right, so panel data, we could collect data on the same individuals at 2 different periods of time. It could be more than 2. But for the purposes of our example, let's say that we collect the first year of data in 2015, and then we return and we collect data from the same people in 2018. We will be able to capture changes in wages over the time period of 2015 to 2018. So this is what that data would look like. All right, this is panel data. All right, so let's look at what a panel data set might look like given the illustration of the example I mentioned a moment ago. So again, we have individuals, their wages and education. However, you'll notice that for each individual, now there's a repeat. We have individual 1 once and then individual 1 twice. So the same person, but 2 observations for that same person. The same thing for person 2. Here's person 2, and we observe them twice. Person 3, again, we observe them twice. Person 4, we observe them twice. Now also notice that we are adding an additional variable. In this case, the year. This measures, or this indicates, the year in which the data is collected. So there's year 1 and year 2. In this specific example, year 1 is 2015, year 2 is 2018. But you can see here that we have person 1, we observe them in 2015, or year 1. Here's their wages and their education level in 2015. And then here's person 1 again in year 2. We measure the same person, but in a different year. Year 2 is 2018, as I mentioned before. Here is person 1's wages in 2018. And here's their education level. You can see that person 1's wages went up from 2015 to 2018. You can also see that their education went up from 12 to 13 between 2015 and 2018. All right, we can see the same for person 2. For person 2, we observe them, we have data for them in 2015, year 1, okay? And the same person, person 2, the same person in the second year, year 2, 2018, we have their wages and their education. Okay, so we have a new variable that indicates the year in which the data was collected. And then we have data for the same person in the second year. Same person in the second year. So now we have 2 observations per person, year 1 and year 2. Okay. Now, this step here, what I've just done, is kind of establishing for you what this panel data looks like. All right. Now, I want to begin and go through a process as I talk and explain how panel data is useful and why it's a powerful tool. And I want to set up for us kind of the assumptions we need to utilize it. And then what I'm going to do is I'm going to go through 2 specific models that we can use on panel data. All right, so that's kind of an outline. So let's jump into that. All right, so when we have panel data, we need to take into consideration that we now have variation across individuals and across time. So just looking back here again, we have variation across individuals and across time. What do I mean by that? Variation. So variation across individuals, that means different people have different wages. Different people have different levels of income. Of education. So you can see person 1 has 12 years of education in the first year, and person 2 has 8 years of education in the first year, etc. So there's variation. There are differences between different individuals in the data. That's normal for cross-sectional data. That's what we have in cross-sectional data. But now in panel data, we also have variation across time. So you can see that even for person 1, their wages are different across time. For person 1, their wage is 15.4. For person 1 in year 2, their wages are 16.5. And so now we have variation across individuals and across time. And therefore, when we conduct an analysis using panel data, we need to take into consideration that when we run our regression, we have variation both in terms of individuals and in terms of time. All right, so then I've written a regression model here just so that I can be clear about subscripts, because these subscripts are going to be important as we talk about panel data. So you see here, I have a simple linear regression model that has a dependent variable y, intercept term, an independent variable x1, another independent variable x2, and then of course the error term. But when you look at this regression, there should be one thing that sticks out to you as being new. And that is that each of the variables has 2 subscripts instead of 1. You can see here on the dependent variable, it has a subscript I and a subscript T. Now, in the past, we're used to seeing the subscript I. The subscript I indicates that this dependent variable takes different values depending on what person it is. So the subscript I indicates the individual. So person 1 will have a different dependent variable than person 2 and person 3, etc. A different value for the dependent variable, I should say. But what's new here is the introduction of this second subscript, T. Here, T indicates the year. All right, so now we have subscript I for individual and subscript T for year or time. So I is typically used for the cross-sectional unit, which is often individuals, and so we have I. And then T is the subscript we oftentimes use for time, which is usually the year. Okay, so we have variation in the dependent variable across individual and across time. Same thing for our independent variables and our error term. So let's try to make this more clear, just to make sure that we understand these subscripts, or these indexes, because we need to be very comfortable with these subscripts as we go through the rest of the lecture. So let's just look at this example regression where we're regressing wage on education. And I want to make sure that we understand what these subscripts mean. So I want to just think about this, and then I want to look at a data set, and we'll just make sure that we understand it. So so when I have this subscript, I and subscript T, this indicates that wages are varying across individuals and across time. So now let's just look at a couple questions. So if I asked you, what is wage subscript 1, 2? That means wage for person 1 at time period 2. Can you find that on this data set? Wage for person 1 in time period 2. Where would that be in this data set? This is just to make sure that we understand these subscripts. Where would we find that? What is the value? What is the wage value for person 1 at time period 2? All right, if you've selected this one, you're correct, 16.5. What about the wage for person 3 at time period 1? Can you find that? Person 3 at time period 1, if you said 19, you're correct. All right, what is the education level for person 4 at time period 2? Can you pick that out? If you pick 13, you're correct. All right, well done. That was just a very simple thing to make sure we understand how these indexes work. All right, with that done, let's move forward. All right, now, for us to understand the power and potential of panel data, we need to again kind of review this omitted variable bias, and then we can kind of work our way up, set ourselves up for understanding why panel data is important. Okay, so panel data gives us a powerful tool for identifying unbiased coefficient estimates relative to a standard cross-sectional analysis. To illustrate this, we need to first review the core problem in regression analysis, omitted variable bias. Consider the following regression model, cross-sectional regression model. And so you can tell that it's cross-sectional because it only has an index I. That means it only varies between individuals. There's no variation across time. Okay, so we have just a simple cross-sectional regression model here. It looks very familiar, I'm sure. Now we know that beta 1 hat, our estimated beta 1, will be biased if the x variable, if the independent variable, is correlated with the error term. All right. We also know that the error term contains all the information for variables that are excluded from the model. We know that x will be correlated with the error term if there exists at least one variable zi that is omitted from the model for which these two conditions hold. All right, this should all look very familiar. The basic idea is this. The beta 1 hat estimate, the beta 1 estimate, beta 1 hat, will be biased if x is correlated with the error term. X will be correlated with the error term if there is a variable that is omitted from the model. We'll call that variable z, and that variable satisfies these two conditions. The two conditions are z, the omitted variable, must be correlated with x, and z, the omitted variable, must be correlated with y. If this omitted variable z is correlated with both x and y, then my estimate of beta 1 hat will be biased. My estimate of beta 1, which is beta 1 hat, will be biased. Okay, so omitted variable bias is a serious problem because we frequently have some omitted variable z that is unobservable. So this is a problem. Omitted variable bias is a problem because we very frequently are going to have omitted variables. And we're very frequently going to have omitted variables for which we do not have data. That means they're not observed in our data set. We don't have data on them. They're either truly unobservable or we do not observe them in our data set. If that's the case, then we will have omitted variable bias in our standard cross-sectional regression. All right, but now panel data is a powerful tool to help solve this problem, and we'll see why. All right, so how does panel data help us to solve the omitted variable bias problem? All right, now to answer that question, I'm going to go through quite a number of slides here, and we're going to kind of work our way up, kind of build some different concepts. Okay, so consider the following regression model using panel data. All right, so this is just the same model, but now we have a panel data set, and so we have variation across individuals, I, and we have variation across time, t. So we now have observations for x and y that will vary by individual I and time period t. This regression, as stated, will likely suffer from considerable omitted variable bias. We will now incrementally demonstrate how some or all of this bias can be removed using panel data. All right, so the first thing we want to notice is that this model omits a control variable for the passage of time. We know that x changes over time, so admitting the passage of time will result in omitted variable bias if time also affects the outcome variable. Therefore, we first include a time variable. So one of the first things that we'll do is make sure that we control for the fact that time is changing in our data set. we'll introduce a new variable, t, where t, and notice, t has a subscript only of t, not I, doesn't vary across I, it only varies across t. All right, where t subscript t equals 1 if you're in year 2, and it equals 0 if you're in year 1. And so this t variable is a variable that is capturing the passage of time. All right, that will help. That will be an improvement over this original model. So adding a control variable for time can allow us to determine how the dependent variable changes over time. However, we may still have omitted variable bias. In fact, we almost certainly will. But now this will begin to allow us to see the great advantage of panel data. So here we go. The great advantage of panel data is that panel data can allow us to control for a particular kind of omitted variable bias. To see this, we will disaggregate the error term into two components. All right, so we have this error term. This error term varies. It varies across individuals and across time. And what we're going to do to illustrate what we're able to do using panel data is we're going to disaggregate this error term. And we're going to disaggregate it into two different terms. We're going to say AI, all right, so this variable AI, and this variable VIT. All right, we're going to take this error term and we're going to decompose it into these two different components of the error term. Okay. Now, what does that mean? What does this mean to disaggregate the error term? What we're saying is that the error term, let's go back here. What we're saying, this error term, remember, the error term captures all the information from all the variables that are excluded from the model. Remember, the error term captures all the information that is excluded from the regression model. Now, with panel data, we can imagine that some of that information that is excluded from the model, which means is captured by epsilon, by the error term, some of this information that is excluded from the model varies only across individuals, not across time, and other information varies across individuals and varies across time. And so what we're doing is we're decomposing this error term into different components. So the different components work like this. There is one component, so a part of the error term is composed entirely of variables that do not change over time. That means as time changes, the variable doesn't change. And so we call that this AI. So AI accounts for all omitted variables that vary across individuals but do not vary across time. So AI accounts for all omitted variables that vary across individuals. That means they're different between people, but they do not vary over time. They're different between people. That means they vary between people, but they do not vary over time. So one example of this, let's say that we did not observe the sex of an individual. So they could be male or female. Now, that variable varies between individuals. Some people are men and some people are women, but it does not vary over time. It does not vary over time. That means if you go from 2015 to 2018, the male in 2015 is also a male in 2018. The female in 2015 is also a female in 2018. So this AI accounts for all the variables that are like that. All the variables that change between people, that may be different between people, but do not change over time. All right, so AI accounts for that. It varies across people, so it has an index I, but it does not vary across time, so it does not have an index T. All right, and then this VIT accounts for all omitted variables that vary over time and across individuals. Okay, so any variable that varies between people, that means different people can have different values, and it varies across time. That means it changes as time goes on. All the omitted variables that vary across time and across individuals is captured by VIT. All right, so just recapping here. The error term in this regression accounts for all the omitted variables. It captures the information for all the omitted variables, everything that's excluded from the model. And what I'm saying is that this error term, we can say that this error term is composed of two parts. All the omitted variables that do not vary across time, so that's AI, and then all the variables that do vary across time and individuals, and so it's VIT. All right, VIT varies across individuals, I, and time, so it has a subscript T. All right. So these error terms allow us to see why panel models are so powerful. We can now distinguish between different kinds of unobservable characteristics. Okay, so remember, the epsilon captures the error term, captures all the information that is omitted from the regression. That means it's capturing all the information from omitted variables. All information from the omitted variables, even the and especially the unobserved omitted variables. All the variables that are omitted from the model that we do not observe are captured by the error term. And so now, when we decompose it into A and V, we can see that A accounts for all the unobserved variables that do not vary across time. And V accounts for all the unobserved variables that vary across individuals and time. All right, so now I want to make a really important distinction here and make sure that we're defining these terms. I want to define two different kinds of unobservables. Now, if you remember, in the past, I've talked about observables and unobservables. Observables are variables, it's information that we have in our data set. An observable variable is something that is capable of being observed and is in our data. An unobservable could be something that is literally, it cannot be measured, so it's literally not observable, or a variable that is not in our data. That means it's not observed in our data. Okay, and we know that all that unobserved information goes into the error term. But now what I'm saying, so before I've defined observables and unobservables, now I'm coming back and I'm going to define two different kinds of unobservables. Two different kinds of unobservables. The first kind of unobservable is called a time-variant unobservable. Time-variant unobservable. So time-variant unobservables are factors that change over time. They are time variant. They change over time. They vary across time. So time variant varies across time. Time variant varies across time. So an unobservable that varies across time is a time variant unobservable. And all time variant unobservables are captured by V. All right. And now I also have time invariant unobservables. These are unobservable factors that do not change over time. Unobservable factors that do not change across time. So these are captured by AI. Okay, two different kinds of unobservables. It's very important to recognize what these are and to make this distinction. Time-variant unobservables, factors that change over time, and time-invariant unobservables, factors that do not change over time. Okay, so let's just give some examples to make this more clear. Okay, let's do an example. So let's go back to our wage example. And we want to identify the impact of wages, of education on wages. So we have this this model that we could run using panel data. We can see that wage varies across individual and time. Education varies across individual and time. We have our error term, and we also have a time term, so a term that accounts for the passage of time. In this regression model, we only have two independent variables, and so there are going to be quite a number of omitted variables in this regression, quite a number of variables that are ending up in our error term. So now I want to think about some of these possible omitted variables, and I want to think about which ones are time variant and which ones are time invariant. All right, which ones are time variant and which ones are time invariant? All right, so just give us a little exercise in terms of understanding these two different concepts. Now notice here I'm saying time invariant omitted variables. I could also say unobservables, but I'm just right now I just want to specify the distinction between time variant and time invariant, and recognize that in this particular regression there are a lot of omitted variables in this error term. Okay, they may or may not be observed. Okay, so time variant variables. So let's think. What are some variables that are going to differ between people and differ across time? So one example might be experience. So that means as time goes on, people gain more experience. So experience will vary across time. In 2015, people will probably have less experience than they have in 2018. It's hard to imagine it going the opposite way. Okay, so experience varies across time. It also varies across people. That means different people have different amounts of experience. Okay, marital status. So marital status might change across time. Obviously, it changes between people. Some people are married, some people are not. But it also can change across time. Single people can get married. Married people can get divorced. Okay, so marital status can change across time. It's time variant. It varies across time. The number of children. Number of children can vary across time. As you go from 2015 to 2018, people can have more children. And so the number of children that someone has varies across time. Various economic indicators can change across time. The economy can grow at different rates at different times. And so these are all variables that will change across time. They're time variant. They vary across time. And these are also all variables that are omitted from our model. Okay. What about time invariant omitted variables? So what are some time invariant variables? Variables that do not change across time. What are some variables that do not change across time? Well, how about ability? Now, this might be debatable, but we might be able to say that someone's ability, someone's innate competencies don't change. Some people's innate competencies do not change over time. And so that might be a time invariant variable. That means it varies between people. Some people have some people just have different levels of ability. But it does not change over time. That means my innate competencies are the same today as they are a year from now. Okay, or intelligence. We'd say IQ. We might argue, and this is debatable, but we might argue that people's IQ, their latent level of intelligence, doesn't change over time. They might change their level of education. They might change the amount of knowledge they have, but their innate intelligence doesn't change. Now, it'll differ between people. Some people have a higher IQ, and some people have a lower IQ, but it doesn't change over time. We can argue that, and someone might argue that it does, but we might be able to argue that it doesn't. The city of residence, well, that might change, and so that's debatable. It depends on the time frame. The city of residence might change, but it might not. Home country, that won't change. Where somebody is from will not change. Where they were born will not change over time. It will be different between different people, but it will not change over time. Okay, so here are some examples of time variant and time invariant omitted variables. So if these variables are not in our data set, then these will be time invariant unobservables, and these will be these are time variant unobservables. These are time invariant unobservables. Okay. So now, so we're building our way up. We're working our way up. So I'm saying that panel data is really it's a powerful tool, because when we use panel data, we can dissect our error term into these two components. All right. Well, it's not yet clear exactly why that's so powerful, but I will show you as we keep going. All right. So now, what do I want to do? Well, let's take this disaggregated error term and put this back into our original regression here. All right, so this results in the following regression model, which we can call a fixed effects regression model, or a fixed effects model. You'll notice this is the same standard model that we had before, so it's this model, except now we're plugging our disaggregated error terms in for epsilon. Okay, and now this error term that accounts for the time invariant unobservables, or the time invariant omitted variables, this AI, we call this the individual fixed effect. So an individual fixed effect is a term that accounts for all the variation in the dependent variable that does not vary across time, and is thus fixed across time, which is why it's called fixed effect. It's a fixed effect. It's fixed across time. We call it an individual fixed effect because it varies between individuals and is fixed across time. Now, in this lecture, I'm going to pretty much exclusively talk about these kinds of fixed effects, individual fixed effects. You will find when you do research that you can also have other fixed effects. You can use fixed effects for different types of variation in your data, but for now, we'll stick to this. So this fixed effect variable, this AI, it varies only for individuals. It captures all the variation in the dependent variable due to differences across individuals, but it's fixed across time. All right, so this AI term, it accounts for all the variation in the dependent variable that is due to differences across individuals. All right, that isn't captured in the regression model. So it accounts for all the variation in the dependent variable due to differences across individuals. All right, so it's very significant to notice this individual fixed effect and differentiate it from the other error term. Now, so here we go. We're building our way up. We're building our way up. All right, I hope that the anticipation is building. Dr. Gallenstein, why is panel data so powerful? Why is it so useful? Okay, so we're getting close. The power of panel data models is that it allows us to control for this AI. It allows us to control for the time invariant unobservables. So if we control for AI, then we will not have any omitted variable bias that is due to time invariant unobservables. We will not have any omitted variable bias that is due to time invariant unobservables. We eliminate one kind of unobservable variable, and therefore one potential source of omitted variable bias. Okay, so the power of panel data models is that it allows us to control for this AI. It allows us to control for and eliminate all the time invariant unobservables. Now, in the past, when we've worked with a regression model, with a cross-sectional regression model, we have only been able to control for observable variables. We've only been able to control for variables that we include in the model. So we're only able to control for variables that are observable. You can remember this also from when we discussed propensity score matching. When we use propensity score matching, if you remember, the first assumption is selection on observables. That means propensity score matching only works when I can assume that basically that my only omitted variables are observable variables, and therefore I can account for them using the data in my data set. All right, that's a very restrictive assumption. It's very restrictive when I can only rely on observable information, on observable variables. What panel data allows us to do, that's why this is so powerful and so interesting and so exciting. I hope you're excited. Okay, why this is so significant is that we can use panel data to control not only for observable variables, but also for time invariant unobservables. We can control for everything, for all the unobservable variables that vary across time, or that do not vary across time. That means we eliminate an entire source of potential omitted variable bias. We eliminate an entire section of our error term. That's quite significant. Okay, so let's try to make this more clear. So in panel data models, we can control for AI. We only then need to worry about omitting time variant unobservables. Okay, so if we think that we can use other independent variables in our data set to control for all time variant factors that affect both x and y, then we will obtain an unbiased beta 1 hat. That means if we use a panel data model, we're able to control for all the time invariant unobservables, and therefore, if we can assume that we can control for the time variant in unobservables, the time variant factors, if we can assume that we can control for all the time variant factors using independent variables in our regression model, then we are able to get an unbiased coefficient. All right, so panel data models allow us to eliminate an entire section, an entire portion of our omitted variable bias. All right, so let's go back here and let's apply this to our example. So the impact of education on wages. All right, so we have this regression model again, except now when we're looking at it, we're disaggregating the epsilon into the two component error terms, AI and VIT. All right, now we've got some time variant omitted variables, and we've got some time invariant omitted variables. So time variant omitted variables is experience, marital status, number of children, and I changed this last one, professional network. Okay, and then time invariant unobservables, we're saying ability, intelligence, city of residence. Like I said, that one you could easily see that as a time variant one because people can move between cities. Okay, and then home country, which is definitely a time invariant omitted variable. Okay, so these are some different variables, and so what we can do is this. We can include the independent variables that are time variant, that means they change over time. So here are the time variant omitted variables. So if we have data on experience, marital status, the number of children, some measure of people's professional network, things that change over time, all right, we're going to include those in the model. We can include those in the model. Oh, I'm realizing that I need to give a T here. There we go. All right. We can include all these time variant independent variables in our regression model. And then we can use a panel data model to control for AI. And if we do that, then we will get an unbiased estimate of beta 1, which is what we want. So if we include independent variables for all time variant factors and use a panel data model to control for AI, the time invariant factors, then we will obtain an unbiased beta 1 hat. All right, so then this is a powerful tool. All right, so next we will see two kinds of panel data models. There are others, but we will focus on two in this class and in this lecture. These models will demonstrate how we use panel data to control for AI. But real quick first, let's just be clear about an assumption that we're making. So for panel data models, for the ones that we use in this lecture, to produce unbiased estimates, you must assume that we have selection on observables and or selection on time invariant unobservables. So let's relate this. The independent variable of interest is not correlated with the time variant error term after including all the relevant time variant independent variables that you have in your data. So what's that mean? That means that there is no correlation between the independent variable of interest and the time variant error term, conditional on the fact so long as we control for time variant independent variables, this is W, time variant independent variables, and we are controlling for the time invariant factors. All right, so this expression means that the independent variable of interest, xit, is not correlated with the time variant error term, vit, if we control for the time invariant factors, ai, and the time variant observables in our data set, wit. This implies that we do not have omitted variable bias. All right, we can only validate this assumption by intuition. We have to ask ourselves the question, can we make a strong conceptual argument for why we think that the independent variable of interest will not be correlated with the time variant unobservables? All right, that can be hard to do, but that's the goal. You have to make a conceptual argument for whether or not this assumption holds. All right, with all of that said, I will now begin the process and finish the process of explaining or illustrating two different models, two different panel data models that we can use to control for those time invariant unobservables. All right, the first one's called the first difference model, and then the next one will be the fixed effects model. All right, and then after that, I'll talk briefly about standard errors, and then we will get into a Stata demo for both of these models. All right, first difference model. All right, so remember our regression, kind of our regression here, where we have y, our dependent variable, which varies across individual and time. We have t, which varies across time. It's the time variable. X, the independent variable of interest, which varies across individual and time. We have our error term that accounts for the unobservables, the time invariant unobservables, and the error term that accounts for the time variant unobservables. All right, so we first need to recognize that we do not observe AI directly. It is an error term after all. We're saying that this is a part of the error term. We don't observe AI directly. Therefore, we cannot include AI in the empirical regression. That means AI isn't a variable. We don't have the AI variable in our data set, so we can't just include the AI variable. It's an error term. So if it's an error term, how do we control for it if we cannot directly include it in the regression? All right. Well, both of these models are going to show you how. Two different ways of doing it. Let's do the first difference first. All right, so here's our generic regression. The first difference model takes the difference between time periods, time period 1 and 2. And by taking the difference, we will eliminate the AI. All right, so consider the following regression models for when t equals 1 and when t equals 0. All right, so basically we're going to take this model and we're going to first see what it looks like when t equals 1, and then we're going to see what it looks like when t equals 0. All right, so let's do that. So when t equals 1, what does this regression model look like when t equals 1? So first, this is the second time period. So we have y, I, and then the second time period. So it's 2. All right. We have beta 0. The t, if it equals 1, is just 1. And so you have delta 0, delta being the coefficient on t here. So you have beta 0 plus delta 0. Okay. You have xit, this t, so capital T equals 1 when lowercase t equals 2, so because it's the second time. All right, so we have this. We have ai again, all right, and then we have the error term. Okay. Now what happens when t equals 0? Very similar. The subscript for the lowercase t is now 1, all right, but the capital T equals 0, and so you get rid of this delta 0. All right. So here we go. This is what the regression model looks like when t equals 1. So this is basically in the second time period. And this is what the regression model looks like when capital T equals 0, so in the first time period. Now, take the difference. That is, subtract the two models. Subtract this model from this model. All right, so here we find the difference. You have yi2 minus yi1 equals beta 0 plus delta 0 minus beta 0 plus beta 1 xi2 minus beta 1 xi1 plus ai minus ai plus vi2 minus vi1. All right, so reiterating here, and now simplifying, we see that the beta zeros cancel out. We see that the alpha i's cancel out, and we can also pull out this beta 1. So now we have yi2 minus yi1 equals delta 0 plus beta 1 times the difference in the x's plus the difference in the error terms. Now notice that ai cancels out. All right, so here's the big thing. When we do the first difference model and we subtract, all this information across time, the AI term cancels out. So here you can see the panel data. Here you can see that the panel data, by taking a difference, eliminates all the time invariant unobservables. All right, because if you take the difference, the time invariant unobservables cancel out. All right, so then you have this, and now we just rewrite these terms in terms of differences. So yi2 minus yi1, well, that's person i's dependent variable in the second year minus person i's dependent variable in the first year. So this is just the change in person i's dependent variable. It's just the change in person i's dependent variable. So we'll use this delta. This is delta, the Greek letter delta, to represent the change in y. So delta, the change in y. All right, so we have the change in y equals lowercase delta, 0, plus beta 1 times the change in x, so delta x, plus now the change in the error term. All right, so here's the first difference regression. It is composed of the change over time of the dependent variable regressed on the change of the independent variable. You'll notice that now this model is cross-sectional. It is only indexed by I because we've differenced out the changes across time. All right, so we have the change in y, and we have the change in x. All right, so it only varies between individuals. It does not vary across time because the time differences have been removed. All right, beta 1 hat will be unbiased so long as there's no correlation, right, between the change in x and the change in the error term. All right, which is equivalent to the assumption I made before. Okay, that is the first difference model. I'll illustrate that in Stata. All right, fixed effects model. Basically, the fixed effects model, we do pretty much the same thing, but just procedurally different. And there are some subtle differences between the two models. The fixed effects model is much more common than the first difference model, and I would recommend using it in most situations. So let's continue. And you'll notice that we do a very, very similar thing here. All right, so here's our original regression again. The fixed effects model differences out the mean of each variable over time, and this eliminates AI. All right, so we're doing a very similar procedure here to get rid of AI, to get rid of the time invariant unobservables. So consider the above model where each variable is averaged over time. So that means let's take this regression and imagine that we calculate the average for each of the variables. So the average y variable across time. So we're averaging it across time. We're averaging it across time. All right. So we take the average of the y variable across time, and so we get y bar I. So this is the average dependent variable for each individual across time. All right, and then here this is connected to the intercept. So it's basically beta 0 times 1, and the average of 1 is 1, so here we go. And then here's the time variable. The average of the time variable across time is just, again, the time variable, so there's no change here. All right, and so now we take the average of the xit variable over time, and so we get x bar I. Okay, we take the average of the AI variable over time, which this does not vary over time, and so it remains the same, no change when we take the average. And then finally we take the average of the error term across time, and so we get VI bar. You can see now in this regression there's no variation across time. So in this model there's no variation across time. We're taking the means. Then what we do is we take the difference. So basically we take this model and we subtract this model from it. All right, so here is our difference model, and we can simplify it. All right, and so what we do is basically we just simplify this down, and when you look at it, beta zeros cancel out, delta 0 t cancels out, so these cancel out, AI cancels out, and what we do is we take this y minus y bar, x minus x bar, and v minus v bar, and create new variables that we call y, and we have these two dots to basically represent that it's the d-meaned y. So y minus the mean is y with the two dots, x minus the mean is x with the two dots, and then v minus the mean is with two dots. And so now you'll notice here that AI again cancels out. So here you can see that the panel data, by taking a difference, eliminates all time invariant unobservables. All right, so again we are eliminating all the time invariant unobservables. And here is the fixed effects regression. It is composed of the d-meaned dependent variable regressed on the d-meaned independent variable. What do I mean by d-meaned? I mean it is so the dependent variable minus the average across time. So we are removing the mean. We're removing the average. And so that's why we're calling it d-meaned. The d-meaned dependent variable and the d-meaned independent variable and the d-meaned error term. So this is the fixed effects regression model. Notice that this model is still panel data. It is indexed by I and T. All right, so the fixed effects model removes the time invariant unobservables by subtracting the means of each variable over time. Because the time invariable factors do not change over time, the mean is the same as the observation, and they are eliminated from the model. All right, so beta 1 hat will be unbiased as long as there's no correlation between the d-meaned x and the d-meaned error term. All right, a couple final points before we do standard errors. We're close to the demo. All right, two quick points, or hopefully quick. All right, so panel data models discussed here will include only time variant independent variables. That means if you include independent variables in your regression, you will only include variables that vary across time. You will not include variables that do not change over time. You will not include time invariant control variables because the panel data model will absorb those effects. All right, so when you're picking out variables to go in a panel data model, in one of the models that we're showing you, a fixed effects model, you will not include independent variables. You will not include independent variables that do not change over time. All right, that's point number one. Point number two is just a couple of wrapping up points. The panel data models that we've discussed here will not include time variant independent variables that change linearly with the change in time. I think the best way to explain that is to use a couple examples. But the point is this: there are some independent variables that do change across time and you still won't use them. You won't include them in your regression. Let me give you some examples. So for example, if year one, let's just say that year 1 is 2015 and year 2 is 2016. All right, so we have 2 years of data, 2015, 2016. If you did that, you're going to run a fixed effects model, then you will not include variables such as age or experience in the regression. Age will increase by 1 between years. And so the change in the age variable is identical to the change in time. Right? So age does change across time. It is time variant. It varies across time. But age varies across the exact same, it varies in the exact same way as time does. If one of my panels, one of my years is 2015 and the other year is 2016, then age will change also by 1. Year is changing by 1 and age is changing by 1. And so we will not include age because it's changing by the exact same amount as the change in time. All right, so that's the first thing. Now, why not experience? Well, this is debatable, okay? So we can debate this. But likewise, if the vast majority of your sample gains 1 year of experience between year 1 and year 2, you cannot include experience because the change in experience will be identical to the change in time. So my point here is this. Let's say that you're doing this regression model and you have experience as one of your variables, but every single person in your data set increases their experience by 1 between 2015 and 2016. That means nobody takes a year off, basically. If everyone's level of experience goes up by 1 between year 1 and year 2, then you would not include experience because it's changing linearly with the change in time. It's going up in time by the exact same amount as time is changing. All right, so you wouldn't include that either. Okay, so those are just 2 final points. All right, lastly, standard errors. I'll just go through this quickly, and then we'll get into this data demo. All right, so when we're using panel data model, we must be careful to estimate unbiased standard errors, just as in the standard OLS models. So remember when we did standard cross-sectional regressions, we talked about heteroscedasticity. We needed to control for heteroscedasticity, or else we might get unbiased. We might get biased. We might get biased standard errors if we didn't control for heteroscedasticity. All right. However, given that panel data has a time component, we must also be careful to avoid serial correlation as well. So heteroscedasticity is when the variance of the error term is correlated with the independent variables. We've talked about that before. Serial correlation is when the error term is correlated with itself over time. All right. We're not going to talk extensively about serial correlation, but we just need to remember that because there's a change in time, there's an additional component of possible bias in our standard errors that we need to control for. Just in practice, and we could go into tremendous detail on this, but I'm just going to kind of mention what we do in practice. To solve these problems in panel data, we use robust standard errors. And these robust standard errors are just a little bit different than what we did. The robust standard errors do control for heteroscedasticity, but we use a special kind of standard error that will allow us to control for the serial correlation as well. And so what we'll do, as you'll see when we do the fixed effects model, is that we will use cluster robust standard errors that cluster at the cross-sectional unit. Okay, I'll show you what that looks like in the data. All right, so with that said, let's do some panel data in Stata. All right, so what we're going to do is we're going to do fixed effects regression. We're going to do fixed effects regression. All right. We're going to do fixed effects regression first, and then we're going to go to the first difference regression second. I know we're going in the opposite direction of what I did in the lecture, but I have what I did in the slides, but I have my reasons. All right, so let's go ahead. First, now that we've got our data, okay, first let me just point out wage FE. I'm using the wage FE data. All right, I'm using the wage FE data, the wage fixed effects data. All right, I'm using the wage fixed effects data. All right, so here we go. The first thing I want to do, all right, actually stepping back. The purpose of this regression, let's come over here. Let's just be clear. This is a panel data set. We want to use this panel data set to estimate the impact of education on wages. The panel includes variation across individuals, just like a standard cross-section, and it includes variation across time. In this case, we have 2 years of data. So we have data on 505 individuals collected for 2 years, 2015 and 2017. All right, so that's what this data looks like. We want to use this. Now let's visualize it first. I want to make sure that we understand what panel data looks like. All right, so here's panel data. All right, so here's our data set. We have a variable here that indicates for the individual. Now, perhaps I should take a moment. In the past, at times we've had data sets that have an ID variable, and other times we haven't. In the past, when I've used this wage data set, I have not had an individual ID. An individual ID is just a number that uniquely labels a specific person or a specific time. So in this case, the ID number, this is a unique individual ID. So that means when the ID number equals 1, that is person number 1. That is a person. That is one person. When the ID variable equals 2, that means it labels person 2. All right. When ID variable equals 3, that means person 3. So these numbers, they don't have I wouldn't even call this a categorical variable, although perhaps you could. It's a label. This variable just labels your data. Okay, so that means you never include the ID variable in a descriptive statistics table. Okay, if you ever put together a descriptive statistics table, do not include the ID. All right, the ID is not. It's not technically a variable in the way that we would think. You don't include it in your regression. The ID variable labels the information in your data set. Okay. All right, so we have the ID for individual. All right, and then we have this variable for year. This indicates the year. So 0, we can come over here and look at it. Equals 0 if the data comes from 2015, and equals 1 if the data comes from 2017. All right, so here we go. What we have here is we have person 1 observed in 2015, so year 0, or 2017, year 1. All right, and we have their information for these different years. So we have person 1's wage in 2015 and person 1's wage in 2017. We have person 1's education in 2015, and we have person 1's education in 2012. We have their experience. We have their ethnicity. We have their gender. We have whether or not they're married. We have the GDP growth rate in those years. We have their network connection. We have their IQ, whether or not they work in the service sector, manufacturing sector, agricultural sector, etc. All right, so we have information for each person for 2 different years. And so we have variation across individuals. That means our information differs between different people. And we have variation across time. That means for each person, we have variation across time. Now, as we look through this data set, we might be able to see what variables we could consider to be time variant and time invariant. So time variant variables would be variables that change over time. Time invariant variables are variables that do not change over time. Okay, so year changes across time. Obviously, it's the year. Wages are going to change across time. So this is a time variant variable. It changes across time. It's time variant. Education level will change across time. So that's time variant. Experience will change across time. So that's time variant. Ethnicity, will that change across time? No, that is time invariant. Will gender change across time? No, that is time invariant. Will marital status change across time? Yes, it can at least. People can go from being single to married or being married to single. And so the married variable, The married variable is a time variant variable. It changes across time. GDP growth, does that change across time? Yes, time variant. Your network connections, the level of network connections, that will vary across time. All right, so it's time variant. IQ, we're going to say that IQ doesn't change across time. And so IQ stays the same for each person across time. So that is time invariant. Time invariant. Does not change over time. What sector of the economy you work in, that will change over time. People can switch sectors. So that's time variant. So we have three different sectors here. We have the service sector, manufacturing sector, agricultural sector. Okay, so just looking through our data, we can see some different time variant and time invariant variables. Now, obviously, we have omitted variables or missing variables. Obviously, there's other things that affect people's wages that we don't have data for. And those things that are omitted, those things that are missing from our data set, these unobserved variables, they could be time variant or time invariant. Okay. All right, so that's what our data looks like with a panel data set. All right, so then let's run a regression. First, let's do the naive model. What's the naive model with panel data? The naive model might be to just run an OLS regression of wage on a bunch of independent variables. We want to know education, so we do education and experience and non-white, and female, and married. We just include some variables here. GDP growth, network, IQ, service. Okay, so the naive model doesn't take into account the fact that we have panel data. So the naive model does not account for the panel data. It does not account for the fact that we have variation over time and across individuals, and it does not take advantage of our ability to control for time and control for time invariant unobservables. All right, so it's just a straightforward regression. So we can run this. We can run this and see what we get. Let's see. Let's increase this. Oh, you know what? I'm looking at the wrong do file. I apologize. Here we go. This. Looking at the wrong do file. Here we go. Let's run this thing. All right, let's just don't save. Let's open up another do file here. All right, now let's run it. Here we go. All right, so here we go. So here's our regression. We find education is positive and significant. We find ethnicity is negative and significant. We find GDP growth is highly negative and significant. IQ is positive and significant. Okay, so we find a bunch of stuff. But now, will our estimates be biased? In the naive model, we have not accounted for or controlled directly for time. Okay, so time will be an omitted variable. So time will be an omitted variable. So we'll probably have omitted variable bias. Well, why is that? Well, because time probably affects wages, and time also probably affects the amount of education that people have. As as time moves forward, education probably goes up on average, and so the correlation between time and education is positive, and I would assume the same also for wages, and so we'll probably have some upward bias. All right, so we've omitted variable bias here. But more importantly, in the naive model, we have not controlled for time invariant unobservables. Therefore, if we think that there are some time invariant factors that are omitted and would be related to wages and education, then we will have omitted variable bias. Okay, so do we think that there are any factors that might be omitted from this model? Any factors that are time invariant, they do not change over time, but are omitted? I gave two in the lecture, so possible examples of time invariant omitted variables. So two possible examples could be ability. Now we might say that IQ measures ability, but maybe not. And then we also could say country of origin. Okay, those are two things that are not going to change over time, but could have an effect on wages and education level. And so this model is not controlling for those two things. And so we'll probably have omitted variable bias. So this won't work. So let's do a fixed effects model. All right, and now I'm just going to show you how to do this in Stata. All right, I'm just going to show you the commands. We're not going to do this by hand. First, what we do is we do a command called xtset. In this case, what we're doing is we're setting our fixed effect. We're setting our fixed effect. All right, so let me explain this. Step 1, set the fixed effect. All right. The fixed effect is the level is the observational unit that we control for. Basically, the observational unit that corresponds to that AI variable that we had in our lecture. All right, so in this case, xtset ID. All right, in this case, we want to control for all variation between people that does not change over time. All right, so we use ID. This ID variable indicates for the individual. All right, step 2, specify the fixed effects model. All right, so here we go. We do xtreg. We put our dependent variable. We got a control for the time. And then we have our independent variable of interest. And then, all right, so now, remember, you can only include time variant variables. The time invariant variables will be controlled for by the fixed effect. All right, so let's go through it. Can we include education? Well, yes, that's our independent variable of interest. What about experience? Now, in the lecture, I mentioned that we can include experience if the change in experience is different than the change over time. In this example, we have 2 years have passed between the first data set and the second. If every single experience variable goes up by 2, that means everyone just gets 2 years of additional experience, then we wouldn't include experience because it's changing at the same rate as the time. So let's take a look. Let's just get an idea. All right, so 2 years have passed. And so if the experience level goes up for each person by 2, then we need to exclude experience. So let's see, do we see that? So for person 1, experience goes up by 1 year. For person 2, experience goes up by 1 year. For person 3, it goes up by 1 year. For person 4, it does not go up at all. For person 5, it goes up by 2 years. Okay, so no problem. Experience changes in a way that's different than just a linear change over time. So we can include experience. All right, can we include non-white? No, that's time invariant. Can we include female? No, that's time invariant. Can we include married? Yes. Can we include GDP growth? Actually, we won't include GDP growth because the average annual GDP growth is the same in 2015 as it is. I'm sorry. The average annual GDP growth is one variable for 2015, and it's one variable for 2017. So that means it will be perfectly multicollinear with the year variable. So we cannot include GDP growth. All right, what about network? Yes, that can change over time. So let's do network. IQ, we're saying that's time invariant. It doesn't change over time, so we can't include it. What about the sector of the economy? That can change over time, so we can include that. Let's just do service. All right, so now then we need to specify a couple more things. We put FE, that means fixed effect. FE means fixed effect. And then I mentioned to you this different error term thing. We need to use robust standard errors, and they need to be clustered at the observational unit. So we're going to do VCE, that's just a code for a different kind of robust standard error, cluster ID. All right, so there we go. Let's run these two things. This is going to give us our fixed effect estimate. There we go. This is going to give us our fixed effects estimate. Okay, now let's see. Why was education dropped from the model? Let me take a look. Why is education being dropped from the model? It's because education looks like it's going up by 1 for every year. That means I didn't code, when I created my education variable, I didn't code it very well. So that's a mistake. I'm just going to edit this later, but let me see here. Gen, all right, gen, let's see, gen, rand equals round, r uniform, 0, 1, okay, all right, replace C, equals ADUC plus rand. All right, now. Oh yeah, that's perfect. Okay. Okay, so here we go. So we've set this up. We have xt set ID, and then we have xt reg, and now all we do is run this. So you see our naive model here. Now we're going to run this fixed effects model. All right, and here we go. Here's our fixed effects model. All right, here's our fixed effects model. We have our dependent variable. We have all of our independent variables. Year is highly significant, so that means wages are going up over time. That makes sense. We have education, and now we should be getting an unbiased coefficient on education as long as we think that there are no omitted variables that are time variant. So time variant omitted variable, or time variant relevant omitted variables. All right, so it's significant at the 5% level, and then so on. All right, nothing else is significant. All right, so our coefficient estimate is 0.23, and it's significant at the 5% level. Those stars mean significance. Well, let's just write it out. Significant at the 5% level. All right. Significant at the 5% level. Okay. All right, so our coefficient estimate is 0.23, and it's significant at the 5% level. Now, the question is this biased or unbiased? And now that is going to be based entirely on whether or not we can make an argument for whether or not we have controlled for all the time variant unobservables. Are there time variant unobservables? Are there things that we do not include in the regression that are changing over time that will be correlated with education and with the wage? We'll talk more about the intuition for this in class. All right. So if we think, so let's assume for now that there are no relevant time variant unobservables. If that's the case, then we would say that an additional year of education causes wages to increase by $0.23 per hour. Okay. All right, so there we go. This is lecture number 15, panel data, fixed effects model. Now, I am going to switch over. All right, now I'm going to switch over to a different data set and illustrate the first difference model. All right, so this one over here is going to be the first difference model. All right, now, to use a first difference model, we need to have data that's just a little bit different. All right. This data, so when we use a first difference model, basically it has the same information, but it's just organized differently. In the last data set, we had the data that was basically stacked on top of each other. So for each individual person, we had 2 observations, and it was and they were different observations by year. Now, what we have is basically we've organized our panel data in a different way. All right. So for each person, for each individual, we only have one observation basically. And so we have only one row. Okay. But I have 2 versions of each variable. I have the 2015 version of the variable, which I just call wage, and 2017 version of the variable, which I call wage 17. I have the 2015 variable of education, and I have the 2017 variable of education. 2015 variable for experience, 2017 variable of experience. So you can see I have the variables set side by side. I have the variables set side by side to each other instead of stacking them basically. I can organize my data in 2 different ways. All right, I've organized it this way so that we can do this first difference in a little bit more intuitive way. All right. Okay, so here we go. First difference. All right. First difference. Now to do a first difference model, the first step, so step 1, is create the difference variables. So create the difference variables. Alright, so that means we need to go through and we need to generate a difference variable. What I'm going to call delta wage equals the wage in 2017 minus the wage in 2015. Wage D EDUC equals education in 2017 minus education in 2015. Gen D experience, so this will be the change in experience. Let's see, let's make this more clear. Okay, experience 17 minus experience in 2015. All right, generate the change in, I'm going to do network first. I'm going to come back to married in a second because that will have its own unique requirements. So network, so we've got, we've got to put that D there. Got to put that D on it. All right. All right, network 17 minus network. All right, gen. All right, do we do non-white? No, it doesn't change over time. Do we do female? No, it doesn't change over time. Do we do GDP growth? All right, let's skip that one. IQ, do we do IQ? No, it doesn't change over time. Okay, actually, let's go ahead and let's do change in GDP growth. All right, GDP growth 17 minus GDP growth. All right. All right, so here are a bunch of variables. We're creating these variables. They are the change in variables. We don't create change variables for the variables that don't change over time. These are the change across time. All right, so you take the 2017 version, you subtract the 2015 version. All right, so there we go. Now, I skipped one. I skipped married. Okay, I have married equals 1 if married in 2015, and then married 17 equals 1 if they're married in 2017. Well, this creates a unique situation. If I create the difference, just imagine this. If I did married 17 minus married, I would get some very interesting results. So let's just look at the married variable. So here we go, married. Now if I did married 17 minus married 15, I would get 0 minus 0, so that would be 0. 1 minus 1, that would be 0. 0 minus 0 would be 0. 1 minus 1, okay. These are all 0. All right, but now, if we look closely enough, we might find someone that's different. Let's see, is there anyone in here that changes over time? I'm betting that there is. Let's see. Is there anyone that changes over time? Is there anyone that changes over time? If they don't change over time, then this will be a time invariant variable, and we don't need to create a difference. But I think that they're different. I think that we could find an example of them being different. All right, let's see. Let's see. I haven't found one yet, so they're not very different. Well, this might not be the way to show you. Let me go. Well, let's check it. Let's see if these are let's see if these vary across time. Some married, married 17. Actually, these guys have exactly the same mean. They have exactly the same mean. Well, this actually might be a time invariant variable in this data set. This might be a time invariant variable. That means no one got married and no one got divorced. Let's do delta married and let's see. But it looks like they're identical. Yeah, it looks like they're identical. All right, so let's just we'll just verify it. Married 17 minus married. Okay. All right, let's create all these variables. Let's run this. Boom. All right, so now we've created all these difference variables. I'm going to check that married variable. All right, I'm going to check that married variable. Actually, oh, whoops. Some demarried. It's 0. Okay. In this data set, married does not change over time. No one got married and no one got divorced. Okay. All right. So there we go. There we go. we have our change variables. So now what do? We run a we run a regression like it's a cross-sectional regression. So we do reg the change in wage equals the change in education. Oh, sorry, we don't use equals here. All right, change in education, change in experience, change in network, change in GDP growth, and then I thought we would use change in married, but actually in this data set there is no change, and so we exclude that. All right, and then we'll use our robust standard errors. All right, so let's run this regression. We just use ordinary least squares. Okay. Let's see here. Okay, so here we go. We have all of our different difference variables, and so we're just going to run our regression with all of our difference variables. Oh, let me close this down. All right, so here we go. We've got so the change in wage. All right, and we have the impact of the change in education, the impact of the change in experience, and the impact of the change in network, and then the change in the GDP growth is omitted. All right, I'll come back to that in just a minute. A moment ago I hesitated on creating this change variable, but I'll show you why. I'll show you why this is omitted. Just a second. All right, so first let's just notice that here, as long as our assumptions hold, as long as we do not have any omitted variables that are related to wage and education, that are time variant, then these are unbiased coefficient estimates. Or this is an unbiased coefficient estimate for education. So basically the impact of education on wage. All right, so here it is. It is insignificant. Now I will note that this particular data set is slightly different than the other one, and so it's the reason that the result is different is not because the method would necessarily give you different results. Sometimes they do, sometimes they don't. But the reason that this is that the data set's a little bit different. Okay, so then let me just quickly clarify what this delta GDP growth variable is, why this is omitted. Why is it omitted? So let's look at the data set and see. So if you look at GDP growth is the same for every single person. Well, why? Well, that's an economy-wide measurement. The GDP growth in the United States in 2015, and this is the GDP growth in the United States in 2017. Every person in our data set is from the United States, and so this variable does not change between different people. It does not change. It is not individually variant. It is not individual variant. Okay, and so when we take the difference between them, the difference is just 0.6 basically. It's just 0.6 for everyone. It's the same number for everyone in the data set. All right, so then when we include it, what happens is that the delta GDP, so the change in GDP, is multicollinear. It's perfectly multicollinear with the constant term, which is just a vector of ones. And so, as you remember from multicollinearity, if you have perfect multicollinearity, one of those variables needs to be dropped, and that's why this variable got dropped. All right. Okay, so there we go. That's illustrating how to use the first difference regression. Now, in this case, our coefficient estimate is 0.15. We conclude that education has no impact on wages. All right, thank you very much, and I hope that you have a great day.